We are going to resume the conference with a talk by Professor Dr. Mateo Aboy from Cambridge, who is going to present his RQT fellowship project about a quantum leap, about decoding quantum computing innovation, patenting trends, innovation and policy implication, expanded to the theme of this conference, to quantum simulation. Mateo.
Okay, so I'm here to present the project Quantum Leap. This is a project on quantum computing innovation, patenting trends, innovation, and policy implications. This is one of the projects here at the Stanford Center for Responsible Quantum Technologies, and the idea is to apply evidence-based empirical IP techniques to see what's going on in the patent landscape, and then more broadly, the innovation landscape. So the first question we should ask is why? Why are we doing this? What is the need for evidence-based IP studies? Well, as you can see here, anticipating the potential implications of quantum technologies, academia, government, think tanks already started to propose, in some cases, governance and regulatory strategies, in some cases, raise concerns, in some cases, suggest policy recommendations. Our argument here is that these contributions are great, but they can be better judged by examining them in conjunction with empirical data to facilitate evidence-based policy. So that's one. To give you an example, for instance, there was early research that argued that there were concerns of IP overprotection in the quantum technologies and quantum computing field, and proposed even some reforms, right, Mauritz? And the question is, well, where is the evidence? Some of these are testable hypotheses. Now, the project is broadly about mapping the innovation landscape, and patents is not the innovation landscape. It is part of it. Patents are an indication of the pace and dynamics of innovation at an early stage, the invention stage. But it's still useful for us to answer questions such as, well, what has been the patenting activity? What's actually been protected? What is the nature of the claims? Which countries and organizations are leading what? And in the case of especially early deep tech areas, this can be quite useful to then check against some of those policy proposals. Okay, so with that, if you go to the website, this is just a snapshot for the type of questions that we are asking. One, current historical developments as well as current trends for quantum computing. Two, geographical distribution of quantum computing patents, so which countries, organizations are leading. Three, what is the scope of protection? What's actually being protected in terms of IP? Gives you an indication of where you are in the technology. Are these patents more similar to semiconductor patents? Are they more similar to AI? That type of questions. Sufficiency of disclosure. When you look at those patents, what is the nature of the specification? Are these good disclosures? Are they useful? Corporate versus academic patenting trends. Impact of quantum computing patents on industry standards. Open source proprietary technologies, and government policies. So there is a set of areas where it's quite empirical. And the idea is to better understand the current state of the art. What is actually being protected as a step, in many cases, just before commercialization and typically after research. And this findings, the idea is to inform responsible quantum innovation governance and the type of discussion that we are having here. So let me give you a little bit of a peek of preliminary results. Some of them were published in the IIC paper, and then I will expand those for quantum simulation. So we'll go over patent activity, nature of protection, etc. And I'll do some audience participation. So what has been the patent activity, patenting trends over the last 20 years? First question you may ask is, well, how many quantum computer patents are there? So audience, and is the field stagnant or growing if you were to look at just the patents? So audience, any guesses? How many of you think that there are more than 1,000 quantum computing patents per year? Raise hands. Okay, and we have Mark as an expert scholar. You may want to copy. How many of you think that it is, well, the others I assume less, stagnant or growing? Stagnant? Growing? Everybody. Okay, so let's look. right? So we conducted, I'm not going to go over the methodology, and this was for quantum technologies. Let me just go to quantum computing. Actually, when you look at patents where you do have in the claims quantum computing limitations, they are not so many, okay? And there is a period, both of you were right, this was like a quantum mechanical superposition where the stagnant and the growing are correct. There was a period of time, actually, where there was quite a lot of stagnation, very few patents, really around 43 or so a year, and then since 2018, you see growth. Around 64% of the development actually has occurred in the last 3 years, and it's interesting to ask why that's the case, okay? So, as we mentioned, both some periods of stagnation and periods of growth. Okay, good. What is being protected? This is an important question. You will see proposals like, oh, we should apply what we have learned from AI to quantum. But wait a second, quantum is a very different level in the technology stack. Can some of this empirical research inform what are the claim formulations that are being used to protect these inventions? What are they directed to? What do you think? Are these claims more similar to AI patents or IT or something that we sometimes call closer to computer-implemented inventions, or more like semiconductor patents? Audience participation. Option 1. How many of you think that these are very similar or close to AI? A few. How many of you think that these semiconductors? Yeah? Most people do not, do not participate. We did a full technology breakdown. Let me cut to the chase. We did claim strategies. We look at how many patents in the claims had the different components, do natural language processing to do a concept landscape, and review many of these. And what you find is that expert review of the patent specifications, as well as the claims of granted patents, they are indicative of a very early stage. A lot of patents towards the physical realizations, qubit modalities, the enabling technology, how do you do the control, etc. Right? So this is not a mature technology. You have also quantum error correction. Many of these patents actually are nearly indistinguishable from the type of patents that you had in the early stage of the semiconductor era. We are building the hardware. Does that make sense? And so, for instance, if you're thinking about, well, what regulatory framework do I get inspiration from? Is this like AI? That is much more in the application level in the technology stack, or is this much more like well, early semiconductors, CPU, GPU, so accelerated compute, a coprocessor? It's much more similar to that. It's the hardware level to enable the technology. Okay. Owners and concentration, this was one of the inspirations for the study. More or less concentration to classical IT. What we see, actually, is that there is less concentration than in classical compute, meaning you have very small entities having decent patent portfolios and using them to fundraise. We look at temporal distribution of the patents, but overall, we found less concentration than in classical computing. And we also found that it looks like a strong patent protection was more important to the small entities than to the large entities. The large entities do not need the patents to fundraise, right? Priority offices, how does the USPTO and the EPO compare? Blue is USPTO, United States Patent Office, green is EPO. And internationally, we also look at patent offices where you see actually US, and then you see China, where you did not have almost any quantum computing or quantum technologies disclosure prior to 2016, and now leads over the European Union, for instance. So the USPTO as the priority office of choice. Something quite interesting that speaks to that period of stagnation is the patent system incentivizing disclosure. This is an example because, 5 minutes? Okay. Because profits are far in the future, and because the business model is cloud-based, you can keep the technology secret, you should probably prefer trade secrets. And the incumbents present trade secrets. That's the reason why you actually had very little patenting activity. But when your new entrants actually started patenting, the Rigetti, etc., the incumbents also started patenting. So really incentivizes public disclosure, and it looks like most of these patents may be in the public domain by the time this technology is really commercially relevant. So significant incentivizing of public disclosure. What about quantum simulation? So remember, the claims were mostly about physical realizations. What about, well, how many patents do we have in quantum simulation? What is being protected where? What is the quality of the disclosure? You see, again, a lot towards physical realizations, less on quantum simulation. These are small numbers, but it is growing. You can probably not see here, but this is some of the patents that we are closely reviewing for applications in quantum simulation, and then actually applications later on in the panel on healthcare. I will go over, well, actually, what are the applications that you have in healthcare at the research stage, what is being protected, as well as then commercial level. You see leadership at the US and China. When you look at the EPO patents, you see Germany and Britain at the same level, followed by France and the Netherlands. There are some patents, though, where you use quantum computing for medical applications, but they are relatively few, and we can explore them in the next panel. There is a paper that is coming out in the Nature Biotechnology issue, or June issue that we did on the sufficiency of disclosure of medical AI patents, where we examine what was the quality of those disclosures, like how many of those patents they disclose the AI architecture, the performance characteristics, etc. We are doing the same, and what we found, it was not very good disclosures, okay? We are doing the same to assess the quality of these patents. And let me stop it here. I'll open it for questions. I think there are 2 minutes or so. And by the way, this will be expanded then in the panel discussion on applications to life science and healthcare.
Thank you so much for your presentation. Can you talk a little bit about the methodology for the research and how you handled differences in nomenclature, like if people filed a patent but maybe use different terminology because it's such a new domain space? Yeah,
so there's a lot to say, and actually the paper does go in detail over the methodology, but just to give you an example, it is helped. You don't have to do this all through keyword searching, okay? Number one, there are CPC classes on the particular area that have been expanded by the USPTO, EPO, and so for instance, now there is a class for quantum computing that they are, I think you have it here, the CPC defines quantum computing as patterns related to information processing based on quantum mechanical phenomena, so you have that, and you have subcategorizations. So there is oops, I have to go back, that's the next presentation. So that, going back a little bit more to the methodology, I had a slide, allows you to improve not just sensitivity, but the specificity, where you're saying, actually, it's not all automated processing. There is also the work that the human classifiers have done to improve that specificity. Let me see if I... Yeah, so this is not just a keyword search. You do have particular CPC classes that help you to categorize actually which one of these are quantum devices, which ones are nanostructures, which one are, so that helps. But I'm oversimplifying. Yeah. Yes.
All right. So
sorry.
Thank you, Mateo, for your insightful presentation and for being such an amazing co-author. All right, the next segment will be about quantum sensing empowered nuclear deterrence. Dr. Lindsay Rand.
Yeah, so I'm going to be talking about a very specific use case, which is the nuclear deterrence space. And hopefully this will contextualize some of the concern that Ryan alluded to in the national security space about quantum technologies, and hopefully provide some idea of how we can better frame the progress in the technology so as not to, over-alarm people and potentially trigger negative externalities. So I'll briefly go over, why I don't think quantum computing or communication are necessarily the main areas to focus on for nuclear deterrence in the near term. And then I will drill down into, what I think about the quantum sensing implications for nuclear deterrence are, and specifically second strike capabilities. So I do think there are applications for quantum computing and simulation that would impact nuclear deterrence. Obviously, decryption would be potentially destabilizing for offensive intelligence operations and undermining command and control capabilities. And systems optimization comes up a lot in the quantum computing sphere, and this is where you could see streamlining of intelligence analysis or targeting decisions. And also, I think there's a lot of interesting applications for materials science R&D, such as improving stealth capabilities for submarines, or as Ryan mentioned, testing and simulation for things like aging plutonium. But because this is such a nascent stage of development, since these are second-order implications, I think it's very hard to anticipate how these are going to unfold. Similarly, quantum communication is a little bit more of a narrow use case. You could imagine it improving command and control and potentially adding a stabilizing element by ensuring that command and control is not being infiltrated. But again, it's still at a more nascent stage, and so that's why I really focus on quantum sensing. We already have prototypes. Just this year, even last month, BAE announced that it did its first all-quantum inertial navigation testing. And you also have quantum magnetometers and quantum gravimeters, which are being tested as well. So by quantum sensing, I cast a pretty broad net, as in any technology that applies quantum phenomena to improve the measurement of physical systems like gravitational fields, electric and magnetic fields, and even acceleration in time. So the first application, which I'm not going to cover in detail, is really timing. I think that this is a very broadly applicable application of quantum sensing where you could better synchronize satellites and add some security into those systems. But what I think are destabilizing and potentially concerning elements where you're seeing a lot of hype and potentially unwarranted concern is in the navigation space, or specifically for missile accuracy, and then detection and tracking of things like mobile missiles and submarines. And so why do these matter? So just to very briefly cover nuclear deterrence, really the most important part of a nuclear deterrent capability is a secure second strike. And so what the secure second strike signals is that if an adversary were to launch a first strike, you would have a second strike capability to respond and retaliate in an unacceptable way. And under rational actor model, this should mean that there is no incentive to launch a first strike. So by bolstering your second strike, you reduce escalation risks. So how do we make a secure second strike? We secure targets from attack, and all nuclear countries do this. So they bury their missiles underground and with reinforced concrete to protect them from attack. But we also do things like hide targets, so you might put them on submarines or on road mobile missiles. We don't use road mobile missiles in the US, but countries like US and China do, or China and Russia do. And so these provide some security in a layering fashion that we will have a secure second strike should a first strike occur, and hopefully disincentivize the first strike. So where do sensors fit in? Well, if countries believe that precision strike could afford better targeting and destruction of the secure facilities in silos, then you could see that element being perceived as being degraded. And if you can improve tracking and detection of mobile systems, then you might see the hidden targets being degraded. And the policy significance of all of this is if you believe that these aspects of your secure second strike are being undermined, then you really don't perceive any other alternative than to build up your nuclear forces. And so this is leading to a lot of arguments in the national security space to build larger arsenals and potentially even adopt more risky arsenal complexity decisions, like all these novel systems. I can go into greater detail if people are interested. But that add a lot of escalation risks. So what I really wanted to do was say, okay, well, just because you're building these technologies, does it actually afford these capabilities that could be seen as destabilizing? And so I try to really separate the technologies and the capabilities, because when people talk about emerging technologies in the national security space, they really conflate these issues a lot. And so there is this assumption that just because you get a technology or are developing a technology, you're going to get all these destabilizing capabilities. So I, provide more context on what is the continuum of developing a technology and then getting certain aspects of a capability that might be concerning. So to walk through that, I'll just go through my quantum sensing case. So I looked at submarine navigation and missile, or submarine detection and missile navigation. Like I said, the second strike concerns. And I just used publicly available literature on what sensitivities people are getting in the lab setting, which I think is, a pretty generous estimate to how they would perform in an operational setting, so setting an upper limit. And then I used publicly available information, which, in the national security space, there's a lot of classifications that can be an issue per the capability requirements. So for example, with submarine detection, submarines are very classified, obviously, but that's where physics can come in handy. So I just calculated the magnetic signature that a submarine produces. You can just do this with publicly available literature on submarine dimensions and hull composition. And then I just mapped it to what sensitivities people are getting with quantum sensors in the lab. And there's two important things to get from this chart on the right. The first is if you look at the more sensitive devices, which are actually those on the left-hand side because you want a lower sensitivity value. Those are really old sensors. So surfs and squids have been around since the 50s. And the quantum sensors, which are the ones on the right, are really not outperforming them. They just have unique operational capabilities. So all this concern for now is not really warranted as far as extreme sensitivity capabilities. But the second thing to get is if you look at the y-axis, you're seeing detection ranges on the order of 1,000 to 10,000 meters. When you think about transferring a technology to a capability, it's actually very small on the scale of the ocean. So you need hundreds of thousands to 1 million sensors to afford this destabilizing submarine detection capability, which people call transparent oceans. But people might say, okay, well, I don't need to detect the whole ocean. What about just falling submarine? First of all, there are escalatory reasons that make that not necessarily the ideal workaround compared to transparent oceans. And also, if you do persistent tracking, there's a risk that the submarine could perform an evasive maneuver, and then if you don't have transparent oceans, you can't find it again. So it's not quite as destabilizing as the transparent ocean scenario. And I've done some Bayesian search pattern stuff, and there's actually a lot of reason to believe, even with the high-powered sensors, that this is not going to be destabilizing to the second strike. But then also countermeasures are easy and cheaper often than these really extreme sensor improvements. So if stealth capabilities improve, then the detection range decreases as the signal decreases. And there are very cheap ways to spoof, jam, or pulse these sensors such that just working and developing sensors should not be perceived as destabilizing. Similarly, for missile accuracy, I don't have a ton of time to go into this, but there's this weird term called circular error probable. It's how we define missile accuracy. It just asserts that within the radius of the circle, 50% of missiles are expected to fall within that circle. And we've successfully have lowered this EP since the 1960s when ICBMs were developed. And I tried to walk through all of the contributors to this error and then figure out what is quantum sensing going to do? But actually, I didn't really have to do all the error propagation because if you look at the sensitivities, yet again, the quantum sensors are not outperforming the classical sensors yet. Again, it comes down to some of the operational performance enhancements like decreased size or dead reckoning with less drift, but things that should not be perceived as fundamentally destabilizing. And again, you can come up with any number of operability limitations and countermeasure considerations that should reassure you that these are not going to fundamentally allow for the targeting and destruction of missile silos and should not be as destabilizing as people are making them out to be. So generally, my research findings show, I think people want to use the term disruptive or emerging technologies, but In the case of the squids and the surfs, I mean, there's clearly a much longer trajectory, which should give us hope that, those of us at this conference can have time to come up with policy solutions and legal solutions. And it's a more complicated transition if you break apart the technology and the capabilities, which can help alleviate some of the concern around these technologies. And I think more progress is likely, but you can just look at experimental hurdles to try and kind of temper your concern and not become overly alarmist about the technologies. And just to contextualize the state of the technology, well, the Defense Innovation Unit just 2 weeks ago announced that it's going to be funding these sensors, including sensors for inertial mission, which would be navigation capabilities, and magnetometers, and particularly that one on the right is actually set right at the submarine detection capability I showed on that chart. So there is a signal that the government is funding capabilities relevant to the nuclear deterrence use cases, but as I've pointed out, I hope that this would not signal something that should be destabilizing or should be perceived as fundamentally destabilizing for something like nuclear deterrence. Okay, any questions?
Thank you, Lindsay, for that hyper-specialized talk. Then, Min-Ha, you have 2 minutes extra for your own talk, which is about a very important RQT project, the Quantum Criticality Index. And it's about understanding critical raw materials, supply chains needed to make all these fantastic machines in quantum technologies. Dr. Min-Ha Lee.
Thank you very much. I appreciate the Mauritz who organized this wonderful event for everybody. I wish next year also. Yeah, today I read with the different side about some raw material. That is how we expect in the future of the raw material to prepare some real quantum computing and quantum technology. And who is really the quantum technology? Everyone know about the two big players as competing each other very tightly. And one of them is the United States is most very strong in the quantum computing field. And on the contrary, China is very strong in the quantum sensing field. There's two big countries, there is the stand first or second and vice versa. And then people think about that. What is the real application of quantum technology? Here is a good example. Is published in the last months by the Chinese people. They developed a high-resolution radar using the single photon avalanche diode, the gathering the stacked, made by the indium gallium arsenide, indium phosphorus, to detect a very large area. For example, 700 by the 1,500,000 cubic feet around in the field, and detecting the single just plane over there, and then detecting all the materials, construction on the road is real. Then there is a question, and which material and the component or equipment is very critical to produce a real quantum computing, quantum technology? We analyzed several examples of some different type of the quantum computing, superconducting and photonic system and all of that. Here's the example. And here is the example of the 19 materials include wide bandgap semiconductor material, for example, such as some silicon, germanium, and gallium nitride, and then 13 component, for example, the high precision laser control part and cryogenic electron part, with the 9 equipment, for example, dilute refrigerator using as Helm-3 and the high precision electronic control device. This is all of some materials, component, equipment, very critical part to produce some quantum computing and quantum technology. Okay, and let me show the first the materials. And what is the critical raw material in quantum technology? Here is some list of the material mostly used in the quantum technology, 28 elements. And some of them is covered by the United States Critical Raw Material Strategy announced in 2022. It's marked by the green, the square, almost covered by the United States strategy. But some of them is missing from the United States Critical Raw Material Strategy. It's marked by the pink. For example, strontium, moly, cadmium, and selenium, helium, phosphorus also. And then what is come from this kind of material component and equipment from over the world? And you can see here this example of the material is most of the material to produce the quantum technology come from China, for example, and others the component, high precision laser or high frequency equipment is come from the Germany of the component or the equipment from the Switzerland. Yeah, everyone know that the critical part to produce the quantum computing materials, equipment, and the component is spread out globally. Then, how will we decide which one is most critical? Which means the level of critical. And for example, here's a material and the component equipment to produce quantum computing. And those are commonly used in all type of quantum computing, the photonic, supercomputing, ion trap, whatever, then should be very important. We call the critical level 1. But not all type of the computer use this kind of material component equipment, but they use commonly more than 2 types, then you can replace by another alternative resource, but there is no alternative resource, then should be critical level 1. But even we can replace by alternative resource, it monopolized by the single country. For example, China and Russia. That is also should be critical level 1. And yet, this kind of DCM flow model based on the vulnerability of the critical part to produce a quantum computer. And I want to show you the example of the critical level 1 material of all of the 28 the element, the molybdenum. Why we select the molybdenum is the missing from the U.S. critical raw material strategy, and then I think it is very important to produce some semiconductor and quantum technology. And 2021, the White House, they announced some supply chain investigation and announced the report, which one is very important to supply chain, revitalizing the American manufacturing industry. And in the report, we see the critical raw materials diagram, you see here, and it's mostly analyzed by the net importance reliance of the material from the outside and China. And you see here the left bottom side corner is the molybdenum is 0, that important reliance, which means quite a secure perspective of the United States, really. And when you look at the molybdenum metals intercontinental trade flow, and you see that China is the largest export country to the Netherlands, and also second largest country export to this material to the United States. Even in Russia, they also export a large amount to France through the Estonia. It's quite the dynamic, actively international flow from the China. And also the dependency to some important of the United States of these materials is 30-70% in 2022. 37% is quite high, but it is not the net reliance. Why this kind of mismatch of this kind of data? Because most of the molybdenum is traded using some paramoly, which apply to the steel making. But we don't need that one. In the quantum technology or semiconductor, we need some high purity metallic type, are marked as the yellow. And as you see here, the last 10 years, this kind of important material from China is 5 times increase every year. So the supply share of this kind of molybdenum metal by U.S. import in 37, as I mentioned, from the China. So we needed to update this kind of critical raw material strategy, the graph. And how about to think about other raw material which used for quantum technology? Cadmium, helium, tellurium, selenium, but rare earths, heavy rare earths, is same. Here is a summary of the reliance of critical raw material in quantum technology to import from the outside, mostly the China. Yeah, some of the materials, the gallium, the yttrium, strontium, tellurium, is reliance to China import from some outside of the United States is more than 90%. Without these kind of materials, you cannot produce any of some quantum components. And some of them is less than some 50%, but still quite high. So we try to expect which one will be the risk in the future, and to prepare minimize the risk, then how? So we try to develop some quantum criticality index based on the data resource to minimize the risk by discovering vulnerability in the critical raw material supply chain. But there is some challenge point because quantum technology is immature industrial technology compared to some other semiconductor industry or the battery industry, which means they have a high uncertainty. It's 55% uncertainty in some industry or some supply chain. Not my theory, is published by the McKinsey & Company's report in 2021. So we try to increase the certainty of this quantum technology by using the AI. Because in the material science field is quite a common methodology to enhance the data set using some machine learning of the real data set. And some accuracy of this kind of method is high, pretty high, it's in 94%. For this one, to develop the new quantum critical index, there is a team is Stanford Center for Responsible Quantum Technology with the Korean Institute of Industrial Technology and one of some Korean university spin-off of the company also. Here's the overall concept of how we developed the QCA project. It's first, we selected the core parameter to make a risky in the future or a new feature of the quantum technology. And then we harvesting data from some data source, most of the database. And then we set up some rule-based analysis to get some real data set. And then based on this real data set, we trained the AI to get some more the data. And then we use some two different type. The machine learning supervised is first we need to check the machine learning or AI works well or not. And finally, we hand over eventually the unsupervised machine learning. It means the AI is trained by themselves to get the real data and the quantum technology. Okay, then people think about why we need the AI. Just we can simulate by the current the equation or database the models, because when I look at this kind of developed quantum critical index, we have to use some huge number of data. It's 10 to 4, 10 to 24. It's impossible to control. I will show the example. And here's the methodology of how we developed the criticality. We selected three different groups of some parameter: vulnerability, national security, and supply chain risk. And each of the group includes some lot of parameters. For example, the vulnerability includes multiple common usage and sustainability and monopolized by the supplier. And also supply chain risk, they include some parameters such as political stability, environmental, social regulation, and national security also, critical level. And this kind of parameter also represented by the data from the indicator, we call the indicator. Here is the example of the parameter indicator which we use to develop the QCI. You can see here some indicator has included their own data set. So how many the parameter we have to calculate to set up this kind of the QCI. Here the example, the number of parameter is the total is 24, multiplied by the 19 critical materials and the 13 critical component and 9 equipment over across the whole world, around 216 countries with some 7 territorial regions during the last 5 years, and then the data set to handling this kind of the parameters is around 403 million data set. But if you indicate to involve their own some data set around, for example, the World Government Index to check out some political stability, they also include 1,200 some data set. So eventually, we have to handle more than 515 billion data set to get this kind of QCI component. Quite huge. And also, most importantly, we have also the responsive material in the index. For example, is Mozambique. You know, Mozambique located in Africa, and nobody care about that one. But the United States, they imported a lot of mineral from the Mozambique in 2021. It's around 10 billion US dollars. It's quite a huge number. And also, how about Ukraine? It's still war field, but United States is importing some metal from the Ukraine in 2021, around 160 billion amount. It's quite high number because of their resources, they produce something in the United States. So as I mentioned, the indicator, we can calculate the indicator from the database using this kind of the definition and equation. Is quite common to get the lot of the information or calculation. And the overall criticality, we summarize these all parameters from the indicator in the vulnerability, national security, and supply chain risk by the calculating distance from origin and summarize it, and how it is commonly decided compared to in the critical metal or critical component and critical equipment. Okay? Yeah, it is actually the calculation individual overall criticality to anticipate some quantum critical index. The example of the Morley in the perspective will be the US. Okay, is a result. And we selected the 2 different types of critical level of materials, molybdenum and the rare earths, compared to the friendly country, the allies, France, Austria, and the gray country, Malaysia, Indonesia, and also concerned country, China and Russia. Here is a very example of the rare earth is, everyone knows, is very monopolized by the Chinese. But in this overall criticality, China is less important compared to the moly. Moly is much more significant compared to some other rare earths. Okay? So we describe the vulnerability and the critical raw material supply chain. We developed the quantum critical index. So we try to extend the analysis, include the physical property or market situation. Everybody interested in the market. There's some people ask me about which one is material is try to stop. And apply the analysis in overall the other materials and components. So we are presenting the QCI by next year about the material, component, equipment, and whatever you want in the country also. Thank you very much.
Thank you so much, Min-Ha, for that brilliant project. Now we have one more talk before lunch. It's about an FDA for quantum technology, so like a QTA. Professor Glenn Cohen and Alexandra Waldherr.
Okay, so I'm talking about a paper today. It was like a cooperation, as Mauritz and Glenn already hinted at, and it's about an FDA for quantum technology, where we try to translate a globally understood and stable functional framework for regulatory to the quantum technology So in the last 7 years, quantum technologies have seen a quite stark rise, especially in 2G quantum technologies. And as a quick kind of categorization, you can think of them as in 6 groups. So there's quantum simulation, there's quantum computers, there's quantum algorithms, there's quantum cryptography, quantum networks, and quantum sensors. And we kind of gave this grouping depending on the literature that was already there, and also by looking back into history, which of the big findings were there, and made kind of a timeline of the previous historical development. And from this, I want to give you a quote, because when we look at this, the question now becomes, how can we regulate all of these huge things? And the quote that I have is, the greatest challenge to any thinker is stating the problem in a way that will allow a solution. And for this quantum stuff that we saw, it's like very hard to cover this broad range of topics in one regulatory framework or get regulators to think about it in a nice way. So this is our abstract, and I won't read everything to you, but I will just highlight the important parts. The problem at the moment with quantum technology, especially 2G quantum technology, is that legal and ethical guidelines are not really there, and the educational barriers are very high, as well as the communication barriers between different actors in the field are immense. So therefore, we propose a phased regulatory framework where we put phases to it. I will explain in one later detail. And we try to design a framework after the FDA clinical trial phases, because those also scale from lab size to the market size. And we gave analogies with 2 examples, one actually from the squid that we previously mentioned before in the paper. So a few axes by which you can kind of decide on different categories of quantum technology is that you can divide them in first-generation quantum technologies and second-generation quantum technologies. First-generation quantum technologies utilize quantum effects that are kind of preset by nature. For example, in an atomic clock, there's like the cesium atom, and you specifically use a frequency that's not really changing. In second-generation quantum technologies, you actively operate and manipulate at the stage while you're doing stuff with the technology during your operation, which makes it a little bit more critical and also sometimes more fragile as a technology. Another axis you can think about is to decide between experimental and hardware technologies and between theoretical and software quantum technologies. For example, a qubit would be a hardware thing, and a quantum algorithm would be a software thing, and quantum computing is like comprising both of them somehow together, but for a regulator it will be important to differentiate because he will have very different aspects to look at. Also for educators it will be important to know if we are have experimental things to bring to young people or theoretical advice that we give to young people when we build curricula. So if we want to define what a good responsible quantum technology now is, we can think of like this turtle, which we are built under the C framework, so it's like a sea turtle. And those of you who have been here last year know it already. We have not lost it. So a good responsible quantum technology is a technology sound idea. It is a unique idea. There should be responsible documentation available that should be reproducible, because if it's not reproducible, it's kind of bullshit. It should be transferable between systems and between different problems. Otherwise, it's useless for societally impactful applications. There should be legal rules developed, and there should be educational material freely available. And if you look at the technology, at the early stages, you will only be able to tick the first marks, and the later on, you will be able to probably also have legal rules and educational materials. So this gives a trajectory of maturity, like a maturity checklist for technology. And from this maturity, we decided that probably a phased approach is a good idea that we can look at for quantum technology. And if you look at the drug, from the bioscience side, we see that FDA has learned from a lot of failures in the history and become a very good thing of how we can structure regulatory for a new technology. And in clinical trials, where you take a drug from the small-scale laboratory to patient groups that should be safe and effectively impacted positively from a drug, we first start with phase 1 trials, which means we look at healthy patients which don't really show symptoms, so therefore we can have an idealized, stable system. From this, we scale up to phase 2, where we first go into the real patient groups, so we apply to an actual problem that we would like to solve. In phase 3, we scale up to big patient groups, do subgroup analysis, and therefore we kind of give really good statistical data, confirmatory data, as a huge data package, which we again give to a regulatory authority. And the regulators work with this data package, and then can decide, are the societal things well solved? Are there ethical rules or ethical risks? Can we give this technology to the market? And if they say yes and authorize it, it goes to the market, it lives there, and during its life cycle, we still monitor actively its safety. And for quantum technology, it could work exactly the same. So if we would have an FDA for quantum, we would have first in quantum technologies. And this is where most things actually at the moment are. You can imagine it sitting in a lab, like a new qubit technology. A lot of academic labs are trying to find new algorithms, new quantum technology at a small scale. But here, often only the experimental side or only the theoretical side that I mentioned before are kind of researched actively in. And then if both things kind of try to combine and come together, for example, a qubit gets also a good theoretical, physical, mathematical foundation, then we get like this mathematical proof that the technology is really a sound technology. And we get from the experimental side the kind of implication that yes, we see experimentally that it also works, not only on paper. So paper and lab go together, and then we come to phase 2. And if phase 2 concludes well, then we come to probably some industry picking the idea up. And then in phase 3, the industry scales it up to application use cases on bigger problem sets, on subgroups of problems, and tries to apply it. And then we don't have it yet, but it would be nice that they make a good data package for educators and for regulatory authorities, and therefore we term this FQA for Federal Quantum Agency or whatever, that they can look at. And if they say, yes, it's okay, it can go to society in like a very open sense, and when it is in society, educators as well as society can get feedback onto the documents that are produced, and the companies together with the users can kind of advance the technology. So in a more philosophical and big framework, there are a lot of aspects that have to go into this paper. So for example, apart from taking this FDA analogy in the phased approaches, there are many learnings from bioscience and gene technology that we can include into thinking of how to regulate also this new class of technologies. There will be probably race dynamics. We already see that this like as closed as possible is a kind of thinking that is there in quantum technology, but may not be very good for global cooperation. If we want to have a race, yes, we can have a race, but maybe cooperation is better. Ethics often stands in causality in young fields where there is a race, when people race for power, when companies race for power, or when global nations race for power. So therefore, we think it is very necessary that to provide a structure and knowledge in an exchange to make a mandatory registration and documentation of quantum necessary now by federal agencies. For example, clinical trials have to be put into the database. We do think that quantum approaches should also be put into a database with minimal information to keep intellectual property safe, but still put it somewhere so that everybody knows where we stand. And from the philosophical framework, this gives us the opportunity to look where we are standing now and then decide from the regulatory side, are these standings applying to the ethical, legal, and societal goals and values that we have. And this relates very closely to the 10 principles of RQT that Mauritz is currently, for example, working on. The open questions and the criticism on the framework are, of course, how can we educate regulators to work with documentation that comes from QT companies? There are very few quantum experts in this world. And how can even one specialized regulator cover this broad range of the 6 different classes that are shown at the beginning? Is it possible? Which education for quantum technology and engineering is already out there? Whose academic institutions provide such people for example, a federal agency to recruit? And then the question is, which power should be given to companies? Which power should be given to users? Because we don't want to over-regulate. We just want to exchange information in a structured way. And from this whole framework, we can just say, like, everything is vague to a degree until you try to make it really precise. And we try to make it as precise as possible by putting it into kind of a workflow. So you have theoretical and experimental parts coming together, going through phases. Each phase produces a standardized document, and we give some example templates for how these documents could look like. These documents go to educators, which can then develop educational material for the public. After phase 3, regulatory checks have to be made. Things have to be put in the database, and the database is exchanged with the public with barriers, of course, to guide intellectual property well. So the precise steps for regulators and legislators to do now is to make the registration of quantum technologies binding by law, to discuss and define the quantum trial phases in international consortia. Therefore, we have a good structure in place. Then to incorporate overarching agencies, most probably on a national level, like the FQA, to coordinate, audit, and monitor the database so that the exchange of information is guided to be very good information and not over-promising and not under-promising. And then to provide targeted funding from seeing what isn't there in the database, from seeing which experimental parts need a theory and which theoretical instruments need experiments, to provide funding and be there as like the regulator who stands behind the good technology that is providing societal value for the future. Thank you.
Thank you. We take a few questions.
Do we have any questions?
Or criticism?
Please.
Suggestions?
So 2 questions, quick ones. One, let's see algorithms. I do not see them as software. This is pure math. Think about Peter Shor algorithm. Will people doing pure mathematics have to register in your phase 1? That's one. And associated, in the case of the FDA, they are protecting, safety and efficacy. Here, what is the risk that you are protecting? What are your safeguarding goals? Yeah? And isn't this like trying to regulate, say, the microprocessor or the GPU in the case, or math?
So it might, like when we're thinking about math, I think one of these things where we kind of thought about safety and efficacy is like we want the safety to be the theoretical theory that is very sound and stable, and then we want to have the efficacy, like the experimental evidence that it's also working in real life. So it's a little bit a different thinking about safety and efficacy. The framework that we want is really about good information in place in kind of a database that allows for good implementation of policy and for good kind of going and cooperating. Does this make sense? And answer your question?
Maybe I'll just add, so the other question, but maybe I'll just add, just as FDA has a risk classification, it doesn't necessarily review every application that falls within its ambit. Think about the AI guidance flag. I think what we anticipate is that a mature regulator would be able to set conditions for what would require merely registration, what would require registration and soft look review, what would require hard look review. And I don't think we purport to kind of get to the substance of that here, but more suggesting this would be like a rational thing for an agency to kind of approach the problem. I don't know if you have anything with that.
One more question.
Okay.
Yeah.
The back, the young lady in the back?
The young lady in the back. Sorry, the young lady. Yeah.
I guess building on Mateo's question is, I think those are two different things. Like in the quantum algorithm where you have pure mathematics and it's not an empirical study, like you either, for other things you either have a benchmark, you hit it or not, and then for some pure mathematics algorithms, even mathematicians struggle to understand verify proof. There might be, lean, formal verification efforts, but we are not there yet. Like I think that as an initial phase, phase 1 or 2, is a bit controversial to me.
Okay, we take the feedback, definitely.
Thank you so much for stress testing our framework. Let's have lunch now together, and thank you, Alexandra, for your wonderful presentation.
Ein Liebchen wohnt so weit von mir.
you.